The next two reactions we're going to talk about are called Friedel-Crafts reactions. And Friedel-Crafts reactions are another form of electrophilic aromatic substitution reactions. Again, remember that that's adding an electrophile to a benzene ring, substituting out one of those aryl hydrogens. There are two types of Friedel-Crafts reactions we're going to talk about. The first being alkylation, the second being acylation. And this really explains itself most when we actually do the chemistry and go through the mechanism, because if I'm saying we're adding an alkyl chain to a benzene ring, it's a little bit ambiguous since we have this alkyl chloride and aluminum chloride. So let's jump right in. If you need to review electrophilic aromatic substitution, or at least a general mechanism of how these take place, go ahead and stop this video and watch the Intro to EAS, Halogenation, Nitration, and Sulfonation video, where there's a generic mechanism for electrophilic aromatic substitution onto an unsubstituted benzene ring within the first few minutes. Otherwise, let's just get right to it. There's a little bit of a different procedure between secondary and tertiary alkyl chlorides or halides and from primary alkyl halides. So, that being said, though, let's get straight into the chemistry. I think it explains itself best when we just do it. So for secondary and tertiary alkyl chlorides, we're going to get zoomed in nice and big so you can see it. One of the lone pairs from our alkyl chloride right here is going to come over and bond to the aluminum. So now we have something that looks like this. Oh, not Al. Excuse me. There we go. Cl, 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 and then we'll attach that to our alkyl chain right there. Note that this chlorine now has two lone pairs and a positive charge. The next step in the formation of this electrophile. So at this point, you could say, oh, well, we're done. I'm done forming my electrophile. In fact, we're not. So this bond to the alkyl chain. So here's the alkyl chain I'm talking about. If I say the alkyl chain, this is what I mean. These 1, 2, 3 carbons. The bond to the alkyl chain from the chlorine is this right here. This is not another carbon. There's no carbon. This is a chlorine, Cl. Okay? The carbon-chlorine bond will actually break. And that gives us our electrophile now. So, like on the halogenation, sulfonation, and nitration video, I'll just say electrophilic atom. And so, you might be looking at this and saying, okay, well, secondary carbocation, well, there's really no better option, more substituted carbon on each side. You've got your SN1 mechanism blinders on from Orgo 1, and you should in situations like this. So you want to make sure that we're getting a nice, cleanly stable carbocation. And in this case, we are getting the most stable one we're going to get. Obviously, a primary carbocation is very unlikely. It does not happen usually. So in this case, certainly you would not get any rearrangement here or here. You would just have the secondary carbocation. So now that we've drawn the formation of our electrophile, as that is very important, we can now start drawing our Friedel-Crafts reaction with this benzene ring, this unsubstituted benzene. And again, so we're going to be here, we're going to draw our arrow from the middle of the double bond over to that positive charge. We're going to draw our benzene ring now with that substituted piece on there. Okay, so for me at the moment, it's going to be a little bit easier to draw it as an isopropyl group on this carbon. And then remember, you also need to be putting that hydrogen on, right? So we have this hydrogen hanging out. That's what's going to come out and be deprotonated. Of course, we also have a cation, right? Where's that cation? So in the previous video, I drew my substituents here. Now that I'm drawing them here, and it looks a little bit more natural for the isopropyl group to be coming up. We can just put the cation right there. There's no difference. The resonance structures will still be the exact same. And remember that we do need to draw resonance structures. So So anytime these resonance contributors are there, we should be indicating that we know that they're there. I'm trying to draw real nice hexagons for you guys. Real nice hexagons. Cyclohexanes. So you guys can see what I'm talking about, so I'm not spending a bunch of time erasing. So we've drawn our resonance structures now. We've shown the delocalization of that positive charge. Now, since we popped off, so I'm going to come back up here. So we've drawn the resonance structures, cool. We also make, remember, from this formation of the electrophile, we also make this negatively charged species here. So we're going to draw that in here, and I will draw that in a different color. So we have Cl, Al, Cl, so we have 4 chlorides on that aluminum. Put the minus sign. The aluminum-chlorine bond, so you're going to draw the line from the center of one of the aluminum-chlorine bonds. I'm going to choose this one because it's right there. To that hydrogen, break that bond down into, back to restore aromaticity to the benzene ring. So then we get the following product. And make sure it's really clear the difference between a resonance arrow and a reaction arrow. So cool. So that is our major organic product. We also produce here. Here, I'll make it nice and dark. We also get some HCl, and we get our AlCl3 back. So that is the catalyst that we have. Now we're going to do, on the next page, we're going to do the same process, but for a primary alkyl chloride. So we go to the next page. Here we go. So the first step in forming the electrophile is going to be the same. Lone pair on the chlorine attacks the aluminum. We get this. Okay, 2 lone pairs on this chlorine. Positive charge, just as before. And then that puts a partial positive on this carbon right here. And at this point, for primary alkyl chlorides only, this is the electrophilic atom. So only for primary. If you have secondary or tertiary, you'll break that chlorine-carbon bond. In this case, you don't yet. That is your electrophile. Now when we come down and do our reaction, and I'm not going to draw an arrow right yet because I have to draw this in. Because remember, it's our whole electrophile. Right? So the double bond from the benzene ring is going to come in. It's going to attack this carbon. That then prompts the leaving group to leave. So this AlCl4 species, and I should put that negative charge in just so we all are on the same page. So we attack that electrophilic atom, leaving group leaves. Now the arrow can come in. And we draw now that alkyl chain on our benzene ring, right? So we draw our benzene ring minus that 1 double bond. So here and here we put our double bonds. In this case, I will put the alkyl chain there. And of course the hydrogen cation right here. We need to draw 2 more resonance structures. For this, so we will delocalize that positive charge across, sorry, my bad, right there. Don't forget to draw in that hydrogen. Really, really important to show that that's there, not a plus. Resonance arrow, yes. Sometimes I can draw my hexagon, sometimes I really can't. Happens to everybody. So double bond, cation. Nice. So now the same end result is going to take place for the reaction. So this species right here that we created, so from here we made this species. So that will come back in, and I again will draw that in a different color for you. So you can see that the foreign species is coming in. Negative. That aluminum chlorine bond will break, forming HCl. So our major product here is our benzene ring with our alkyl chain attached. And for the sake of saying it, we also get HCl and aluminum chloride. So that is a Friedel-Crafts reaction for a primary alkyl chloride. And actually, just so we can draw the overall reaction, I didn't think of putting that in the notes. So we'll go CO, AlCl3. So that's your major organic product, and we'll actually do that for the previous example as well. Legible. There we go. So AlCl3, crap hexagon. It's okay, y'all. It's okay. It doesn't matter where on the benzene ring you put it, so there's your major organic product there. Again, and it doesn't really matter where you put it. So the next thing I want to say is dialkylation is likely to occur, and it's hard to control. So we just drew the major organic product from this one reaction. Wow, so we have to do it again. Don't worry, we're just drawing the product. We're not doing anything too complicated. So remember, you get this, and I'll put the isopropyl group here, but you could also get Diealkylation, usually in the para position. So remember, if this is our position, our substituted position, one spot away is the ortho, 2 spots away on each side is meta, and the direct opposite position would be the para position. So dialkylation can most definitely happen a lot. So that is a problem with Friedel-Crafts alkylations. Another problem, as we have hinted at but not necessarily talked about 100% yet, really quick. So when we combat this, I should read my own notes. When we to combat this problem, we use a large excess of benzene. So we would get, so if you're writing out the reaction, if you want to show that you're getting one product, excess under the benzene, that tells me that if you draw the product, I'm expecting monosubstitution. There we go. So, any generated carbocation can result in a Friedel-Crafts alkylation. Okay? So, what's the big deal here, right? So, this could give rise to multiple products. Okay? So, if we draw the formation of the electrophile here, and we'll draw that in over here. Actually, no, we'll just do it right here. We have space. Don't worry about it. Sorry for moving the screen, y'all. So we draw the formation of the electrophile. So we get this Al, this tetravalent aluminum chloride. And what I will do is I will actually put the alkyl chain right there to kind of leave it in the same orientation. I was going to draw it on the other side. I'd like to leave it in the same orientation. So then I think you can guess what happens, right? So since it's secondary, that carbon-chlorine bond breaks. We'll show that that's attached. So now we get this. Now, here's where your Orgo-1, SN1 carbocation rearrangement blinders need to be on. Because to one side of this cation, there's it's primary carbon. To the other side of this cation, okay, there's a tertiary carbon. So, a tertiary carbocation will inherently be more stable than a secondary carbocation. So this, let me draw that a little nicer, is entirely possible. So, what does this mean? Well, when we have two different electrophiles, we can get two different products. So, going back, we're not going to draw the whole mechanism for it, don't worry. So we draw in our benzene, right? We go here. We have two products, right? The product from the secondary carbocation. So basically, we would make it look like this, right? So we're bonding it to this carbon right here. So imagine the benzene rings right here, this carbon, another carbon, kind of a vertical line here, and then what looks like what's an isopropyl group, right? But you could also get a rearrangement, okay? You could also get this rearrangement that happens. So you must say, whoops, I want to write, not point. You must say you would get two products from this reaction. And what you would do is you would also draw the benzene ring substituted as such. So, I'm missing a carbon, whoops. There we go. So, if you look, from this rearrangement right here, I've bonded to this carbon. I've just taken this group right here, placed it above because it looks a little bit nicer. Figured we'd put the carbons in the same direction. So those two would be the major organic products. Again, I want to write. There we go, not point. So obviously this is a problem. We want reactions which are selective, okay? We want reactions which are really, really, really selective. So there's another type of Friedel-Crafts reaction, and it's called a Friedel-Crafts acylation. So we're adding an acyl group to our benzene ring rather than an alkyl group. And this, as you will see very shortly, is a much more reliable reaction, and it's a really, really great workaround to the problems at the alkylation. So we can go straight into the electrophile formation. I'm sure you're used to doing this. Arrow from the lone pair of the chlorine to the aluminum. We get something that looks like this. And then, right, so you're thinking, okay, this is a primary alkyl chloride. No. So that's not how we're going to go about this. So yes, in theory, it is primary. But since this is an acid chloride, what we do is, in fact, this bond will break because when we do this, we form, obviously, our electrophile. So double bond to the oxygen stays the same, and we get something that looks like this. And you're like, well, how is this any more stable? Well, it is resonance stabilized, in fact. So you don't have to draw this in every time. So this is stable. It will react like this, don't worry. That's just to show you that it is, in fact, resonance stabilized. So let's go ahead and do our mechanism. We're going to bring in our electrophile, so double bond oxygen. Make sure we didn't lose any carbons here before we go on. So we'll just say, okay, we need 1, 2, 3, 4 carbons. On oxygen, we have oxygen, 1, 2, 3, 4 carbons. We're good. Remembering those lone pairs, positive charge, right? So I'm sure, actually, let's move that positive charge to right here. Because, of course, the double bond on our benzene ring is going to attack the electrophilic atom. We now get to put a different substituent than before, which is nice. So we draw the hydrogen. We draw the carbonyl group with whatever alkyl chain is connected to it. And then you think, oh, okay, so no resonance structures, right? We have a double bond. No, we're kidding. There's definitely resonance structures. So you'll never get out of resonance in EAS. It never happens. Just accept the fact that you'll be drawing resonance structures forever. And also, just remember to throw that hydrogen in there. Otherwise, you're showing that the carbon has 3 bonds. And in fact, that would also be a cation and it would just be difficult. So we know that we say in bond line structures that carbon-hydrogen bonds are implied. In this scenario, you should always, always, always draw them. Just to play it safe. So those are our resonance structures. In the same manner as before, again, remember we form from this step this tetravalent aluminum, which has a negative charge. In the same manner that this happened in alkylations, it will happen in acylations, so that is a good similarity. We will say Cl, Al, so that from the center of the bond to the hydrogen, this bond breaks, restores aromaticity in our benzene ring. And then, so we pop that hydrogen off, nicely. Pop that hydrogen off, we are deprotonating, so we are restoring aromaticity, and we get our major organic product. Now, I said Friedel-Crafts acylations were a good workaround for Friedel-Crafts alkylations. And you're looking at me and you're like, okay, first of all, there's a ketone right here. There's literally a carbonyl group. How is this even close to replacing an alkylation product? Well, I'll tell you. Because, in fact, what you can do is you can use ZnHG and HCl, so zinc mercury amalgamate, HCl, what am I saying? To just completely take off the ketone, which is like, wow, that's fun. So you'll notice, by the way, that I did have the product drawn right here. So anyway, so after we treat it with zinc mercury and HCl, we just get this. So theoretically, right, there's hydrogens here. Yeah. So I'm actually I'm gonna redraw it. You'll know that I like to draw nicely for you. That's much better. Much better. So this is how we can use, so we do an acylation and then a reduction step. And we've basically gotten to an alkylation type product. We've added an alkyl chain to a benzene ring, and we've added it nonetheless at a spot that would have been a primary carbocation. So that is why I chose to use a little bit more detailed of an alkyl chain. Usually I would just do the example with something like this. just to keep it simple, I just wanted to show like, hey, that would be a really unstable carbocation. So, nonetheless, that does it for Friedel-Crafts reactions. The biggest pitfall for people is forgetting things like this. So if you have an exam question and it says, oh, draw the products, you'll draw it connecting at this carbon right here, and you'll say, oh, okay, I'm done. Remember, that carbocation can rearrange to this position right here, and you can get this product as well. So watch out for that. Alkylations are a bit of a problem to deal with sometimes. Remember the difference, again, between primary alkyl chlorides and secondary and tertiary alkyl chlorides, there we go. So in drawing that electrophile, remember that you don't get this leaving group popping off until after the benzene ring attacks this carbon. Then you get that leaving group leaving. Yeah, so that will do it for Friedel-Crafts. Hope that is pretty easy to understand in conjunction with the other electrophilic aromatic substitutions video. I definitely know that this one was longer, even though it had fewer reactions, and you're like, what the heck? I know, sometimes it happens that way. But just remember, so if we're starting with benzene, really internalizing that it reacts very differently than other carbon-carbon double bonds. So you could not pull this off if it was not benzene, or at least at this point. So anyway, that being said, watch out for the next set of videos, which is going to be about nucleophilic aromatic substitution. And that will do it for the video today. We'll see you next time.